All right, so I might be a little bit loopy as I give you this lecture today. And the reason is because I just spent 40 minutes trying to make the lecture just right before this, and it didn't record at all. So I'm a little bit crazy. It's okay. It's okay. Love technology. It's not the technology's fault. It's my fault. Hit the start button, Powers. Okay. Trying to get over myself here. Letting you know I'm human. Connecting. Today we're talking about sig figs, which I love. Significant figures is really cool because what it does is it tells you about the precision of instruments as you're measuring things. And numbers in science are not the same as numbers in math, okay? Numbers in science bring a little bit of extra meaning. So, those poor math guys, they just get numbers, but we get numbers with meaning. So I want to talk about that today. I'm going to be using this little tool here quite a bit to talk to you about what significant figures are and why they're important. Okay, so our objectives here today: determine the number of sig figs and measurements, apply it to calculations, and to distinguish between accuracy and precision. Okay, so why do we use sig figs? What's important about them? Sig figs, sometimes we say sig figs instead of significant figures. It's a lot easier, right? They tell us all the digits known with certainty, the ones we know by actually seeing that is actually hitting that number. And then we also guess one digit. We estimate one digit in between the known marks, okay? So sig figs are going to give us more information than regular numbers do, communicates precision of instruments, and tells us how precise the instrument was that was used to measure the object. Here you can see a nail is being measured, and we kind of zoom in on it. You can see the tip of that nail is right in between two little points, two little measuring points, and I'm going to show that to you here with my tool of measuring. Okay, so if I look at this, I've got 4 tools on this little plastic, okay, what do you call this, rectangular cube. And this tool is my least precise of my tools. It's got just 2 increments, okay? It's got the starting point and the ending point here, and that's all I can do on this tool. If I measure my little marker with this, I'm like, well, yeah, it's about 0.1 meters, right? It's about that far along, and so 0.1 meters, I guess. Well, let's change to a different tool, a tool that's more precise. This tool has 10 points of measurement, and let me measure it there. Okay, well, it's 0.1 plus some, right? And so I can say, well, maybe about 0.12. It looks like it's about 2/10 of the way between that mark and that mark. Now, what was known? What was known was the 0.1 part. I knew I was 1/10 of the way across this measuring tool, and I had to estimate the hundredths place in this case, right? 0.12. So I know 0.1, that's the known. Remember that significant figures always have what you know plus an estimated digit, okay? That was the one that I estimated. Okay, so it's got the known digit plus an estimated digit. So and that's the extra information. That's why this is better than math. We use math, but we're better than math. We have a little bit more information. I now can tell you what I know, and I can tell you what I'm guessing. And if all I did in math was tell you 0.12, you don't know what I'm guessing or estimating. You don't know anything except for 0.12. Yeah, it's better, right? Okay, so now let's look at the next tool. Here I've got centimeters, and I'm taking that to the edge. And if we look at the centimeters, now we go all the way to the edge there, and we can see, oh, I'm at 12 centimeters, which is 0.12 meters. Plus, there's a little bit beyond that. Maybe to a half. Maybe it's 0.125. Oh my goodness! All right. So I bumped up my measuring tool. I got a better measuring tool, and now I have 2 known digits. Okay. So this one and this one are known. And now this is my new estimated digit. Now, you just learned with this number, you learned something about my measuring tool. You learned that this, because of the way we do things with significant figures in science, you learned that this measuring tool I used was better than this one. You all of a sudden knew that I went from this to this. Isn't that cool? Of course, I need to have units on here, right? Meters. So you just learned that I went from this to this. Wow, that's cool. That's extra information hidden in a number. Why? Because we as scientists all realize this and we all want to work that way. Okay, so now we go to the next measuring tool. I'm getting more and more precise in my measuring tools. This tool is even better. If we look at it, okay, I don't know if it'll focus on that for you, but if you look at it, it's now at 0.1, it's at 12 centimeters, and now I've got this, I can see, it looks like 0.12, and maybe you can see it better than I can, but then I've got I think two of those little marks that it goes past, and maybe hits exactly at that, okay? So now I've got, 0.122. I didn't do a very good job of estimating that, did I? That's okay. Give me a little slack. I'm not amazing all the time, just some of the time. 0.1220 meters is now what I've got there. So now all three of these digits, all three of those digits are now known. Why? Because I could actually see that it got past that little part. And then this one is now my estimated. Now, notice that I thought that it went exactly right on that line where it was at the 2, okay? Just remember that when you are measuring things, that you make sure to put a 0 if you think it lands right at that spot, okay? Don't just leave it at 0.122, because if you do, then you're not telling us all the information that we should know. We should know how precise your instrument was. And so I can give you extra information on how precise my instrument was by doing this. Does that make sense? All right. All right. I think you got a good feeling for that, I hope. And let's go on to the next part. All right. So, boom. Yeah, let's say, for example, what information is given by the answer below that might not be true? Now, one of the things that is important to understand here is that your values that you multiply together should not give you extra information. And so what we do is when we do multiplication of things, turn off a little extra light here. When we do the multiplication of things, we're multiplying here. We have to make sure that our final answer is not more precise than our initial measurements. I can't just create information. Now, in math, 97.731623, all those numbers mean something. But in science, those last numbers, they're garbage. They don't mean anything, okay? That's data that's not necessarily true. Because I measured to the 100th place there, the 100th place there, and the 100th place there. How in the world am I going to go all the way to the millionth place in my final answer? I don't have a tool that measures to the millionth place. And so that's why all those numbers there are bogus. They're baloney. Because I cannot get you more precise than my least precise measurements. Okay, so when you are doing multiplication, you're going to see that in a rule here in a second, but when you're doing multiplication of stuff, you want to make sure that you only express answers based upon the least precise that you have here. Okay, or what we actually say is we actually don't talk about precision with these, but we talk about the number of sig figs. So your final answer in multiplication has to be, and division, has to be the same as the least number of sig figs that you have. And so I have 3 sig figs here, 3 sig figs here, 3 sig figs here, and so my final answer has to be in 3 sig figs as well. And so all that information is the stuff that is not necessarily true. Now, could it be true? Yeah, it could be true. But we don't know that. Okay, we don't have a measurement device, a precise enough tool to actually measure that. Cool? Isn't that fun? Fun to see how you can get extra information out of the numbers there. Okay, now these are the rules for sig figs, and I've got some fun little hand gestures I'm going to teach you here in a second. But go ahead and take a second, maybe pause, maybe screen capture, And then you can look at these rules. I'm going to turn the slide off, and then we're going to go through these here in a second. I want to go through each of these hand gestures with you. And so we're going to talk about these rules one by one. All right. So that first rule, and it works usually a little bit better if I've got you guys in this class, because I can sincerely point to each and every one of you, and I can point with my number one finger, my pointer finger, and I can say, you are significant. You're so significant. You're significant. All right. Imagine me walking around the room and telling you that. Well, this is a non-zero digit. This is the number one. It's not zero. And so all non-zero digits are significant. Okay. Now, and I would have you guys do this as well. If you have a sister or a brother in the room, maybe a cat, you can take your other finger as well, and you can now get ready to point to them, right? Point to them. And now let's do this. I've got a significant figure and a significant figure. These are both non-zero digits. All non-zero digits are significant figures. And then look what's between them. Now I've captured some zeros. These are called captured or captive zeros. And so I've got two zeros in between my non-zero digits. Okay? And guess what? I can look through those little binoculars and I can say, you are significant. You are so significant. Oh, right? So zeros that are captured zeros that are in between significant figures, those are significant. Okay? All right, then the next one. I've got a little bunny foo-foo here. Little, what? Bunny foo-foo? Yeah, some of you guys might have known this when you were a kid. You might have heard this from your parents as a little nursery song. And if you do know it, you're welcome to sing with me at home. I usually make all of my students in class sing it. So I guess you got lucky for one thing this year, right? So this is a leading zero. That zero is a leading zero, and it's leading this number two, or maybe if it's two ones, 1, 1, okay? But this is a leading zero. All zeros that lead numbers that are significant are going to be not significant. And here's how we remember it. Little bunny foo-foo. You going to sing with me? Okay, come on, let's sing. Little bunny foo-foo, hopping through the forest, scooping up the field mice, popping them on the head. I know, right? Violent. Sorry, I should have given you a little MA warning there. It's a little too violent. But that's how the nursery rhyme goes. We're just taking that nursery rhyme and we're applying it to significant figures. So you'll remember it. Little bunny foo-foo, hopping through the forest, scooping up the field mice, popping them on the head. Ah! Okay, but what am I saying there? I'm saying that zero, if it's a leading zero, then you bop it, right? It's not significant. The zeros that lead non-zero digits, if they just lead it, are not significant. Okay? All right, let's go to the next one. Again, we'll give you some examples here in a second. The next one, you got to go Spider-Man, all right? Spider-Man was my favorite childhood superhero, and I was, going around slinging webs all the time when I was a kid. But you're going to take your little Spider-Man web-slinging fingers, okay? And we're going to turn it into something that, it's not Spider-Man, but that's okay. Now I'm going to take these two fingers, and they're going to become the two wings to my airplane, okay? What? Yeah, this is a bomber. And so I'm going to take this one and this one, and those are going to be the two wings to my bomber. So this is a point, decimal point, right? It's a pointing finger. You can remember that. Pointing finger, decimal point. This one is a non-zero digit. And so I've got to take these two, and I've got to have them be the wings of my plane. Now remember, a plane cannot fly with only one wing. The bomb is never going to get up off the ground, right? So you cannot be without the point that leads it, and you cannot be without the number, okay? It has to be a zero that trails both the point and the number, because if you don't have both, this thing is not going to go. But if you do have both, if you have the point and you have a number, that zero becomes significant, okay? A bomb is significant, right? So that zero is significant if it follows a point and a number. You can remember that, right? Yeah, sure. That's fun. Okay, so we'll talk about another example of that here in just a second. The last one, rule number 5, you're going to kind of do something goofy here. You ever done that before? This one's kind of a weird hand gesture. It doesn't really work so much as you want it to. But the counting numbers, there's two things here. Counting numbers and numbers that we define as man. Both of those things, if you put those into a problem, they have an infinite number of sig figs. It's supposed to be an infinity symbol, right? Okay, yeah, I know. So counting numbers and numbers defined by man as conversion factors have an infinite number of sig figs. So you don't use them in calculating number of significant figures. I'll show you an example here right now. Okay. All right. Back one. So let's see these as examples. Non-zero digits. Remember, you are significant. Anything that's not zero. None of those are zero. Therefore, there are 4 sig figs there. Okay? These zeros that are in between non-zero digits, right? You are significant. So that 0 is in between non-zero digits. Therefore, that 0 is significant. So we have 4 sig figs in that one. Again, what are you telling us about the precision of our instrument? We've measured each and every one of those components. This is an estimated digit, but these were all measured digits, okay? Leading zeros are not significant. Here's our little bunny foo-foo. Those 3 zeros were leading, okay? Because they lead to 7, then none of those zeros are significant. There's only 1 sig fig there. Just that little 7 is the only thing that's significant. And again, remember that those leading zeros are just placeholders, okay? If you are thinking about it, 0.0007 millimeters is the same thing as 0.007 centimeters. And so all I'm doing here by, I'm just changing, by adding a 0, all I'm doing is changing the unit that I'm expressing it in. And so that 0 is just a placeholder. It's not really telling me anything more significant. Oh, sorry, I said that a little bit wrong, didn't I? Please hold while brain is figuring out technical difficulties. I'm back. Okay. Sometimes you get in front of the class or you get in front of the camera and your brain doesn't exactly work as smoothly as you'd like. Well, there you go. 0.07 is what I was trying to say. Millimeters, okay, 0.07. So 0.007 centimeters is the same as 0.07 millimeters. And let's just be honest. I had to take a second and do a little quick unit conversion because for some reason those numbers didn't make sense until I did the math. So let's do the math. Remember, this was what we learned yesterday. So let's practice it real quick. 0.007 centimeters. How do we do a conversion factor? Well, we say for every 1 centimeter, we've memorized that there are 10 millimeters. Okay. So then if it's 0.007 times 10, well, it's got to move that decimal point 1 place over this way, right? So it's going to be 0.07 millimeters, right? So, even teachers like Powers, who, you'd think are infinitely smart, you've got to do a little math sometimes to get that brain to work out those cogs. All right, so anyway, that's the story for that one. So leading zero is not significant. All you're doing is you're telling me, what your unit is that you're measuring in, basically. Those zeros in front, and this is the same for trailing zeros, if that's all they are. The trailing zeros also can just be placeholders. And when I say trailing zeros in that case, I'm talking about ones that might be like, 70,000 meters versus 70 kilometers, okay? Those two both have just 1 sig fig, right? There's no difference here except for the unit, and so we're just expressing it in a different unit, but they both have trailing zeros, and they both have just 1 sig fig, okay? All right, so let's talk about trailing zeros that have both a point and a number. This has a point and a number, therefore that 0 is significant, okay? 3 sig figs here. Point, right? And a number that it follows. Therefore, that 0 is significant. And because that 0 is significant and that 2 is significant, the 0 in between them, sorry, I can't do that, is significant. Same thing here. This 0 is following a point and a number. Therefore, that 0 is significant, right? And then these 2 zeros become significant because they're stuck in between, right? Captured zeros. Okay, now let's go on to number 5. The counting numbers and the defined conversions have an infinite number of sig figs. Well, remember that count values, for instance, 3 cars. You have to have a car to have a car, right? If I had a car and it was chopped in half, it wouldn't be 1.5 cars. I can't really call it a car because it's not able to run, right? It's not going to be moving like a car. It's not a car if it's only half a car. It's a half a car. So counting numbers, okay? 3 cars, 12 cows. It's like 3.0 infinite, 12.0 infinite. That's how many cars there are. 62 miles an hour is different. That's actually a measurement, okay? So this does not have an infinite number of sig figs. This would, but this doesn't. This is actually just 2 sig figs because miles per hour is a measurement. Conversion factors. Now, this is a conversion factor defined by man. We decided at some point that there were going to be exactly 100 centimeters in a meter. Okay, we were just defined that. And so that's basically like 1.0 infinitely, 100.0 infinitely. They're exact amounts, but that was by definition. So that has an infinite number of sig figs. This, however, doesn't. 1 kilogram being equal to 2.2 pounds, well, when I measure it, it's not exactly 2.2, okay? If I wanted to have a more and more, precise measuring tool, I would get 2.2, blah, 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 and that could go on for a while. But, so this is actually not an infinite number of sig figs. This, in this case, we'd be saying, oh, well, that's 2 sig figs because of the 2.2. However, you're not going to know that for a lot of the stuff we do, right? You're not going to know whether or not it was something that was actually measured or whether it was something that was a value that was defined by man. So, if you get something like that, don't worry about it. Anytime we do conversions in this class, I'm going to assume that you don't have to know whether it's infinite or measured. And so if you get a conversion factor, just assume that it's infinite. Just don't use it to calculate your final number of sig figs, okay? So conversion factors, just assume that they have infinite sig figs, even if some of them don't. Okay, so let's go on to the next thing. And the next thing has to do with multiplication and division. Again, we kind of talked about this already, but in this case, I've got 5 sig figs and I've got 2 sig figs. My final answer here looks like it has 6 sig figs. That's not correct. That final answer can only have 2 sig figs. The rule says that it has to have the same number of sig figs as the factor having the least number of sig figs. In this case, 2. So my final answer here has to be 530 meters squared. Okay? And so 530 would have 2 sig figs. I'd have to round that 531 down to 530. Okay? Now, for the addition and subtraction, it's a little bit different. In this case, we're going to add things up. Okay? So 37.26 meters. 37.26 plus 2.7. Line up the decimal points. Plus 0.0015. 0, make sure I'm far enough out there. You add all those together, and you're going to get 39.9615. Okay? Now, addition and subtraction says that you need to pay attention to the decimal point. Okay? The results can be no more certain than the least certain measurement. Well, look here. I measured to the 100th place here, I measured to the 10th place here, and I measured to the 10,000th place there. So I measured much more specifically there than I did there, much more precisely there. So my final answer, I draw a little line right through here where it's just going to the 10th place. My final answer, oops, too bad I didn't line those up very well. 39.9615. My final answer can only be expressed to that point because that's the most precise measurement I had, okay? And so my final answer needs to be expressed here where I cut it off at that point. Now, the rules for rounding, okay? While we look at the answer here, we're going to go to our next slide. And we're going to talk about rules for rounding. Now, I'm going to tell you these rules for rounding. But I'm going to tell you that these rules for rounding are going to be more complex here that you have to learn than what you actually have to apply. What you actually have to apply is going to be easy. If it's between 5 and 9, you add 1. If it's between 1 and 4, leave it the same. Okay, but I want to show you what the scientific rules of rounding are so that you at least know, even though I'm not going to make you practice that. Okay? Notice that here it says if it's 6 to 9, you round up. If it's 1 to 4, you round down, or you stay the same. But then you've got these 3 instances where it's 5. Oh, what happens when it's 5? What do I do? Well, they came up with a few things to help you figure out what to do with its 5 so that you have values that are not going too crazy, I guess. Let's see what we do here. In this first case, in the real situation, it's bigger than 5. Okay, it's the 6 to 9. And so you would just call this 40.0. Okay, that's how you would finish this answer out. Don't forget the box, right? 40.0. Okay, that's how you'd come up with it. But let's see what other kind of situations we might have. What if we had one of these where it was a 5 exactly, right? And it's followed by non-zero digits. So let's pretend like that was a 5 up there. And so our answer down here is a 5. Okay, now it's a 5 followed by non-zero digits. So what do? It says I add 1. So now it becomes 40.0. Okay, now let's do a couple others. Let's say it's exactly 5. Oh my, okay. So we're going to get rid of that. We're going to add it to 0. So it's exactly 5. Now, what do? If it's exactly 5 preceded by an odd number. Oh yeah, it's preceded by 9. That's an odd number. Therefore, I'm going to add 1. Oh, okay. So this one would become 40.0. What if it's exactly 5 preceded by an even number? Let's say this was a 6 here. And so that became an 8. So what if it's exactly 5 preceded by an even number? Oh, well, it says then that the last sig fig stays the same. So then we would just call it 39.8. Okay, what? Why? Well, again, part of this is just trying to figure out, half the time, it might be a little bit bigger, half the time it might be a little bit lower, but because we don't have enough of a precise instrument to know, let's just say, hey, if it's right at the 5, 50-50, then half the time odd numbers, it's bump it up, and half the time even numbers, let's bump it down. Okay, so it's kind of just a way to work with the world of averages and say, well, let's just try to find the average of life in general. All right, so let's go on to our next thing. That's sig figs. And sig figs, again, tons and tons of fun. Can be kind of complex and complicated, but if you dig into it, way cool. Let's talk about accuracy and precision. I've got 3 dartboards up here, and they represent different forms of accuracy and precision. Accuracy is whether you hit the true value. In this case, we can talk about our bullseye being the true value. Okay? And so these are all hitting the bullseye. And because they're hitting the bullseye, they're accurate. Because they're grouped together, they're precise. So good precision means they're grouping your data points together in this case. And so this is both accurate and precise. Here, I have not hit my bullseye, right? And so I'm outside of my bullseye, but I am grouped together well. So this one is precise, but it's not accurate. This one, you'll notice, has not hit the bullseye, and they're not grouped together. Therefore, this one, not precise, not accurate. Okay? Now, can you think of an example where you might have a bullseye where it's accurate but not precise? This one's tricky. Here's my bullseye. Okay. What if, kind of in the center, what if I had a dart that hit there, and a dart that hit there, and a dart that hit there, and a dart that hit there? Now these darts are all over the place. So it's definitely not grouped together, is it? So that's precise. Is it accurate? Well, not a single one hit the bullseye. But what do we do in science a lot of times? We average. That's why this one's tricky. Because think about it. The average between there and there, it's right there, right? And the average between there and there, it's right there. Okay, so we have basically hit the bullseye with our averages. That's tricky. All right, but there you go. You found one that could be considered accurate but not precise because of averages. Okay? All right. Of course, if you're playing darts and it's actually the game and you're dealing with points, then that has nothing to do with it, right? The points be all over the place. So accuracy, how close measurements are to the true value. Precision, how close measurements are to each other. A precision instrument reliably measures many digits. You might not be able to read that. A precision instrument reliably measures many digits. The more precise the instrument is, the more digits it's going to measure toward, okay? Doesn't necessarily mean it's more accurate, though. Let's look at a couple different examples with the scale. Describe the accuracy and precision of each set of measurements. The true value for each set is 15.00 grams. So now I've got 3 digits here, or 3 measurements here. Whoa, those are kind of all over the place, aren't they? Does it look accurate? Does it look precise? Neither, right? Neither accurate nor precise. Let's look at these. Is it hitting close to the true value? Yeah, look at that. It's only off by 100th, 100th, and 100th. So that's really pretty good measuring, right? That's very accurate, okay? Is it precise? Yeah, these things are grouped together really closely. All right, we got both precision and accuracy with that set of measurements. Here, I'm only off by about 100th again, okay? But I'm way off. I'm off by like 2 and 100ths, all right? So in other words, these things are all close together. They're only far away from each other by about 100, but they're way off from the true value, which was 15, and I'm at, I'm 1.5 away from that. And so this one is definitely precise because they're grouped really closely, but they're not accurate, okay? Now let's look at this one. Which set of data is going to represent balance with gum stuck under a tray? What would gum do? Like, it's sticking there and it's probably got the balance just stuck, at a certain amount every time. It's probably going to be messing it up pretty consistently, okay? And so I'm a really good measurer, but the gum is making it a little bit inaccurate every time. So this would be the balance with gum stuck under a tray. Which one would represent sloppy workmanship in which someone is neglecting to notice other objects touching the scale? Well, I think probably this one, right? Because sometimes, and I've seen this in class, students will be measuring stuff and then the corner of their book is like actually laying on the top of the scale and they don't even notice it, right? Or maybe it got stuck underneath and it's kind of lifting it up, right? So maybe seeming, more weighted or less weighted based upon where that book corner might be at. And so this one is sloppy workmanship versus having a little piece of gum. Cool? Okay, so now we have learned our objectives here. We can determine the number of significant figures and measurements and apply that to calculations. We can distinguish between accuracy and precision. Again, a lot of fun, super useful. Science is better than math, we got getting a lot of good lessons out of the day. But remember that the significant figures, although they might seem a little complicated, are super important. As scientists, we use them all the time. And, I'm going to be honest with you, I don't think I understood significant figures until I started teaching it. So as I was going through school the way you are, I was like, it hurts my head. Okay, so I get it if it hurts your head right now. But you got to figure it out. You're going to be better than I was.